Brad Williams, Frugal Finance. As I mentioned in the previous introduction to swap pricing, we're going to need to match forward rate agreements with the swap price. There's a lot of moving parts in terms of putting all this together in the way of, it's called parity or one price. Just be patient. I'll walk you through how we're going to do this one step at a time. In this particular session, we're going to talk about strip Treasury securities and forward rate agreements. In the previous section, we saw how to compute zero coupon factors and rates along with forward rate factors and rates for the par yield curve. Explicit markets for zero coupon instruments and forward rates also exist. Treasury strips. A strip T-bond is created when a normal T-bond is decomposed into a series of zero coupon bonds corresponding to the various coupon and principal payments that constitute the bond. For example, a 30-year semi-annual coupon T-bond could be stripped to give 60 zero coupon instruments that pay the original coupon payment of the bond plus one zero coupon bond that corresponds to the principal repayment on that bond. Forward rate agreements. There's also an explicit market for forward rates. Contract based on the forward rate is known as a forward rate agreement. Forward rate agreements are typically based on SOFR, which stands for Standard Overnight Funding Rate, a rate which the Federal Reserve lends funds to. Typically, an FRA calls for the exchange of a payment based on SOFR at a future date in return for a payment based on a fixed rate of interest agreed on the contracting date. One can contract to either pay fixed and receive floating or to receive fixed and pay floating. Typically, an FRA market maker will have a spread on the fixed side of the deal to provide a profit margin. For example, consider an FRA market maker who agrees today to pay 6 months SOFR in 6 months in exchange for a fixed interest payment on an annual rate of 5% and a notional principal of $20 million. If the market maker is willing to take the receive fixed side of the deal at 5%, might be willing to take the pay fixed side at only 4.96%. Spreads of 4 basis points are typical in the market. While the FRA expires in 6 months, assume that the 6-month SOFR stands at 5.8%. Payments on the FRA would be the interest rate times the fraction of the year times the notional principal. Receive fixed 5% times half a year times 20 million, 500 grand. Pay floating negative 0.58 times half year times 20, 580. Net payment 80 grand. In this case, the market maker would be obligated to make a payment of 80 grand. In the FRA market, it is customary for settlement amounts to be determined in advance and paid in arrears. The payment based on the FRA in our example would be due 6 months after the date of determination, because 6 months was the maturity of the interest rate being used in the FRA. Thus, FRA based on 3 months SOFR are paid 3 months after the determination date. FRAs based on 6 months SOFRs are paid 6 months after the determination date, and so on. FRAs are quoted in the following manner. Term to expiration in months times term to the end of the period covered by the agreement rate. For example, the FRA we considered above with 6 months to expiration for 6 months SOFR and a fixed rate of 5% will be quoted as 6 times 12, 5%. The first number indicates the month until the FRA expires. The second indicates the number of months until the instrument presumed to underlie the FRA matures, while the difference between the two numbers shows the maturity of the presumed underlying instrument. There is no actual instrument that is delivered. Instead, the presumed underlying instrument is simply an instrument of the underlying maturity that pays SOFR. Instead of exchanging instruments, the profit or loss is settled in cash, as in our preceding example, at 80 grand. The 5% in the question is the fixed rate of interest to be paid in exchange for SOFR. The rates on the forward rate agreement also tie in with the zero coupon yield curve. Assume that the current 6-month spot rate is 4.95%. And consider now the following FRA quotations that imply a rising yield curve. 0.6, 4.9, 6 to 12, 5%, 12 to 18. These are months. 5.1%, 18 times 24, 5.2%. We adopt the following notation. FRA is the rate of interest on the FRA for a period beginning at time X and ending at time Y. FRA of Y indicates spot rate from time 0 to time Y. On the basis of this notation, we have the following. The first task is to find the 6-month zero rate, Z05, 495, 5, 510, 5.2. Find the forward rate if you have the zero rate. This is a very complex formula. I had the assistance of an online service, Simulab, help me out with this. One, I just got stuck in the weeds trying to compute this. Find the forward rate if you have the zero rate. Usually it's the other way around. So we're going to solve this. So y is equal to 0.506. This would be based on y equals the forward rate. So we have z is equal to, this means it's just the 0. 0 to 6 is 1 plus 0.5. That means 6 months here. 4.95. That means the 0 of the first 6 months and the 0 for the second 6 months. Solve for y, where 1.025 equals 1.5068. Y will equal 0.506. And then we're just going to go through, and I did this repeatedly. What's the point here? Note the following equivalence. FRA equals forward equals forward. We will use the forward to refer to the forward rate generically, and the FRAXY to refer to a rate on forward rate agreement. To avoid arbitrage, the two must be equal. We also define the following. FRAC is the fraction of the year covered by the FRA. NP is the notional. We now want to integrate the quotation and payment mechanism of the forward rate market with our technique of bootstrapping to find zero coupon factors. In particular, we need to take into account the fact that payments occur in arrears and that the dollar amount of the payment depends on the part of the year covered by the FRA multiplied times the notional principal. So based on the first FRA 06 is equal to 0.495 to cover the period. From the present to 6 months, the fixed side payment would be FRAC 06 times the timeline times notional equals 495 times 0.5, which is the 6 months, times notional principal. We have not defined the notional principal for this example because the notional principal does not affect the rates on FRAs, just the dollar amount of the payment. Therefore, in general, we're going to ignore this notional principal in our computations of FRA. We can compute the value for the first zero coupon factor as follows. And we did this. Why did I input all this? This is commentary. If you have this zero rate, the 0.2475, you're going to be able to compute the forward rate. I just went backwards. Just keep this in mind. I doodle. This was a doodle. In other words, I was stuck. I wanted to know what the forward rate was if I had the zero, and this is how you do it, okay? I'm off track here. We're going to go back down here. Here is the zero for the first 6 months. We can go back to that previous example. I'm just explaining. I know I went through the first computations rather fast, but this is the first 6 months. Then where FRAC is equal to 0.5 reflects the half year between payments, and FRA equals 4.95 is the current SOFR 6-month spot rate. Back up here, spot rates, 495 is the current SOFR 6-month spot rate. Note that the payment actually occurs at the end of the period covered by the FRA, but is based on the observation of SOFR at the beginning of the period covered by the FRA. The zero coupon factor for the second payment covers 12 months. And given the value of z of 6, we now compute the value of z0 to 12 as z of 6 times 1 plus 5, half year, 0.5, times 0.05 equals 0.02475 times 2, 0.0253 equals 1.506. So there could be a rounding issue here, where 0.5 reflects the half year between payments. 0.05 is the rate of the 6 by 12 FRA. Values for the 18 and 24 month period follow similarly. So we're going to get this 1025. Then we're going to go 1025 F131 times G127 right here. G127 G. So we're multiplying this times this, get this. Remember I said we're going to step forward, then step back. Well, we're just stepping back here, and this is the zero rate. Then we're going to do it again. Look here. This is the formula, 1 plus 0.05 times 0.052. Where's the 52? Right here. Here are your forward rates. Here is the zero rate. And if we go back, if I shrink this, and I go File, New, and we look at this term structure, I think we're going to see some similarities here. So if we go back here, I don't know if these are Treasury bonds. They're not going to equate to the same numbers. Ignore that. But the principle is the same. All we're doing is bootstrapping. This is a bootstrap method. Our numbers won't, see, we're using 495. Numbers won't gel. But the concept is exactly the same, where all we're doing is bootstrapping. So if you're a little confused here, go back here and just look at the format. Look at the formula structure here and the formula structure here. It's the same. That being said, we've computed, here are the zero factors. Here was the question is, if I have the zero rate, can I compute the forward rate? We have 0.6. Let's look at this example here. Here's the first period. We have 1.2475. If we go through here, y is equal to forward rate. So we have 1 plus 0.5 equals 1.2475. That's the zero. So solve for y, where 1.2475 times 1 plus 0.5 times y is equal to 1.506388. We're going to get 1.506. And that should represent, if you compute this, what we're trying to do is find the forward rate for the next period. If you go through all of this nifty little math, and I walk through step by step, I explain it, you're going to see 5.06. And what does this 506 represent? This is the next right here. 506.761, 506.76. And if I extend this out, you can see there it is. There is our forward rate. Many, many ways to San Jose, as they say. Brad Williams. Lots more to come.